Hi, welcome to my attack. Today I'll be demonstrating a DNP3 timing attack where I send a malicious DNP3 packet to an outstation to change its time. I will also explain why this is an issue in the electrical operations industry. In normal electric grid operations, a master station, or GPS, will be sending correct timestamps out to outstations and RTUs to get the correct time. Accurate timing is very critical. My attack will send a malicious DNP3 packet to an outstation. This is important because devices will blindly trust DNP3 and accept whatever packet it sees as trustworthy. DNP3 does not have any way to check if this is fake or coming from a different source. When time synchronization is lost, outstations can report events 5 seconds ahead of time, or whatever time has been changed, and it can cause a lack of situational awareness. This can cause relay coordination systems to be disrupted, as shown. But this can also create cascading levels of effects. First, fault location systems become useless. These systems need exact timestamps from multiple sensors to find where faults happen. With bad timestamps, repair crews might get sent to the wrong places, making outages last longer. Second, automatic load shedding can go wrong. These systems use time-matched data to decide when and where to cut power during emergencies. Bad timing could cut power when it's not needed or fail to cut power when it's critical. Third, power quality checks become meaningless. Engineers need synced data to watch system health, but bad timestamps make this impossible, potentially missing early warning signs of big problems. Finally, figuring out what went wrong after outages becomes impossible. When major blackouts happen, investigators need accurate timing data to understand what happened and prevent it from happening again. This attack ruins that critical evidence. The bottom line, a simple 5-second being off in timing can break the grid protections, cause unnecessary equipment trips, and potentially lead to cascading blackouts and ruin our ability to learn from incidents. Now that we know why it is important, let me show you a demo of the way I decided to go around attacking the grid. Now onto my attack demonstration portion. I'll be demonstrating my DNP3 timing attack against this SCL351S protection relay. This relay is in my home lab, and connected to it I have a network switch that monitors all the packets going to and from it, which I'll show you later. I should demonstrate how the attack is working. In the background here, I have a SCADA system, which is pulling the device for both voltage and frequency, which is over DNP3, and over Modbus it is showing its time in seconds, so we can clearly see the attack working. To start my attack, I'll call Python script. Now, since DNP3 is not the most time accurate, a lot of times there will be other time protocols that might take effect over it. In this such scenario, the relay is configured to use NTP before DNP3 messages. But NTP can be very easily disabled. Enter my relay's IP address here. The cool thing about this program, it can automatically find the NTP servers. I'll talk about this later when it's discovering them. Now I'll set this time to something very obvious so you can clearly see a time change. So now it's automatically detecting the NTP servers. It is doing this by manually connection and viewing when it requests NTP sync data. It'll learn when the servers are in the timeout. This is important as we can precisely predict when we need to send the right packets so we're not overloading the network and we can hide from network detection tools. As we can see, the device tried reaching out over NTP to the timing server, and it failed, as our script has blocked the NTP packet. So here shortly, you will see it expire data. Yep, there we go, there's a change. As you can clearly see, the time has clearly changed, and if you tell it into the device, you can see it also believes the time has changed. Now to undo the attack, it's very simple. We just let it be able to reconnect over NTP, and the time will be brought back. And I'll show you in Wireshark here. So in Wireshark we can see the NTP requests are being dropped, and we can see the DNP3 write commands. And you can see that the timestamp was set to May 5th, 2020 at 12 a.m. And you can see it's failing to reach out to the NTP servers, and eventually once the ARP table on the switch updates, it will allow it to reconnect via NTP and the device will be unharmed. And there we go. The device was able to successfully reconnect over NTP and got the correct time back.